Welcome to this short video about engineers and contractors' ability to influence the amount of environmental emissions from concrete structures. Hi everyone, I'm Nathan. As you all well know, I'm going to take you through this subject. But first, before we can talk about it, we have to know where is really this CO2 emission coming from. And then I will use a short video from YouTube to show you this. So let's roll the movie.
Technically, cement is the heavy hitter. It's the thing that, cements the basic ingredients of concrete, sand, rocks, and water, together into a single useful material. And it's a mean source of planet-warming carbon dioxide. Cement's 1-2 punch comes from how it's made. First, we have to heat limestone, which typically requires us to use lots of fossil fuels, which emit CO2. Second, once we do that, the limestone chemically breaks down into lime, which goes into the cement along with some other stuff, and carbon dioxide, which goes into the air. In most industrial processes, the energy used to run machines and heat stuff up is the overwhelming source of carbon dioxide. But with cement, when the limestone itself breaks down, it releases even more CO2 than all the other parts put together. All told, for every ton of cement we make, almost a ton of CO2 gets released. Today, cement's double whammy leaves it responsible for 8% of humanity's carbon dioxide emissions. That's more than airplanes, ships, and long-distance trucking put together.
So concrete is standing for very much of the emission of CO2 to the world. Almost 8% is coming from concrete structures. And as you understand from this movie, the cement is the bad guy in this picture. So what can we as engineers do to inflect the emission from concrete structures? Well, we can do things that reduce the amount of cement in the concrete. And there's a lot of things that we can do, but I will just go through 3 points that will, as we engineers can inflect on the reduction of emission from CO2. The first thing I want to talk about is the strength of the concrete. As you all know, we are calculating the strength of concrete after 28 days. From fresh concrete. Well, if we want to have a hardness strengthness and don't want to do anything about the aggregate and the water, well, what should we do then? Well, the only thing we can do is put in more cement. But as we see from this table here, if we are calculating the strengthness of concrete after 28 days, that's almost the middle of 0 and 50 here. And as you understand from this graph, the strengthness of the concrete is getting much better over time. After 90 days, it's flattening more out. But from 28 to 90 days, you get a real more strengthness in the concrete. So if we can calculate the strengthness of the concrete after 90 days instead of 28 days, it will do much better for us and much less emission of CO2. So the first point is the time of strengthness of calculation. If we can do this and calculate with 90 days instead of 28, it will help a lot. The next thing I want to talk about is aggregate. Today we are using very much small aggregates. It's common to use GG16. That will say no aggregate larger than 16 millimeters. And also very often we are using reduced aggregate. That will say that we use more cement pasta and less aggregate. And all of these are making us using more cement. As you see from this cut through a concrete structure, you will see all these large stones. Inside these stones, of course, there are no cement pasta. The cement pasta is the glue between the aggregate. And as we have more large aggregate, it will be less pasta needed to glue the aggregate together. So the second point will be use a larger size of aggregate and also much more aggregate, not less, not reduced if you don't need it. The third thing I want to talk about is design, where we as engineers can reflect a lot on how we are constructing. As you see, all these 5 barriers, they are carrying the same load, but they have different goals of why they are built like this. We can, if we make it a goal to have a less emission, we can use our static knowledge to build barriers that can carry more with less stiffness of the material, and then again less cement in the pasta. So think about that when you are doing the construction, to use your static knowledge to make them those static carrying instead of the material. We see it also with slabs. Here on the left side you see a traditional slab with barriers underneath, and that use a lot of concrete. You can use, for instead, a kind of a flat plate slab. That will say it's a slab that's self-carrying, and you don't need these barriers underneath, and then you can spare a lot of concrete. The last thing you see here is voided slabs. What will that be? Well, as you all well know, in the middle of the construction, where the neutral axis is, we don't need that much material to carry the load, because there is no load there. So what voided slabs is that we are making boxes or anything to have voided rooms with nothing inside in middle of the slabs, to take away that concrete that is not needed. So we got whole room that with air instead of concrete, wherein the concrete is not needed. As we see from this table here, if you do different calculations, if you use flat plate instead of traditional construction, you can spare up 8% reduction of CO2. If you use voided slabs, you can even get 28% more reduction. And if you do that together, well, you will get almost 35% reduction of CO2 for each construction, and that's a lot. So design is the last thing I want to talk to you about. Think about emission when you are designing. So when we are coming out as new students, let's do this. Let's think about emission when we are constructing, and we'll try to save the world better. Thank you for listening.